A hypothesis test can tell us if a difference is statistically significant. For example, is a drug effective at helping cancer patients compared to a placebo? However, it doesn't tell us how big the difference actually is. Does the cancer drug increase life expectancy by 10 days or by 10 years? For that question, we need to consider effect sizes. Why can't a hypothesis test tell us about how important a difference is? After all, we calculate a p-value, which is the probability that the difference could have come from a null distribution. Here's the problem. The shape of the null distribution that we simulate is going to be very dependent on the size of the sample that we collect. If we only collect a small sample, then the null distribution will be very wide, even if we do a lot of permutations. As a consequence, we will get a larger p-value and be less likely to reject the null hypothesis. Take the example on this slide. As we increase the number of students whose heights we measure, the null distribution narrows. As a consequence, less and less of it is more extreme than the observed statistic, which is shown in red, so the p-value becomes smaller and smaller. The p-value depends more on the sample size than on the size of the actual difference that we're trying to detect. So how can we know if a 0.5-inch difference in height is a large difference? After all, the height of students within schools will vary by much more than the height of students between schools. This is where we turn to effect sizes. There are all kinds of ways of measuring effect size, but for continuous variables, we are going to use one called Cohens D. This takes the difference in mean heights and divides it by something called the standard deviation. The standard deviation measures how much variation there is in our heights as a whole. If there's a lot of variation in heights in general, then the standard deviation will be large. And when we put a large number on the bottom of a fraction, the output will be small, and so we'll get a small effect size. On the other hand, as the number on top of the fraction, the difference between groups, becomes larger and larger relative to the overall variation, then the effect size becomes larger. So this is a pretty simple and intuitive way of measuring how important a difference is relative to the overall variation in the samples. Obviously, if we have data that is categorical, then we cannot calculate its mean, and we have to measure effect size differently. One option for categorical data is the phi coefficient, as illustrated on this slide. Although the formula is not as intuitive as Cohens D, it tells us the same thing. How big is the variation between groups compared to the variation overall? It's important to report effect size as well as p-values. Here's an example that illustrates why. A famous study of a very large number of patients found that aspirin could reduce the risk of heart attacks. They had a very low p-value in their study, indicating that this was a very significant result and very unlikely to be due to chance. However, the actual effect size was not large. Yes, aspirin reduced the risk of heart attacks, but not by much. And although aspirin is relatively mild, like all drugs, it has side effects. You can imagine that for more dangerous drugs, we would want to know that the benefits of taking the drug outweigh the risks. So in summary, a p-value tells us if a difference is statistically significant from random chance, whereas an effect size tells us how big the difference is compared to the general variation in the population. And as data scientists, we should report both numbers to give a clear summary of any analyses that we do.